Welcome back. We hope that you're enjoying the programme so far. Just a reminder to please reserve the stage chat for any questions that you have for speakers and use the events chat for general commentary. Now I'd like to introduce our next speaker. Facundo Domínguez is here to discuss how to apply the upcoming GHC language extension LinearTypes to manage references to values in a foreign language. Please welcome Facundo.
Hello, everyone. Welcome to my office space at Montevideo. I want to present you the contribution of my daughters to HaskellX that you can appreciate on my background. The tag is not that good, well, at least you can appreciate the artwork. So going to business, there's a new language extension that will come in the next version of GHC, which is called LinearTypes. And since long, it has been said that LinearTypes is useful. It's a useful tool to do programming with resources. What we are going to see today is we are going to take a look at how the current incarnation of LinearTypes that comes in GHC will look like in practice. So our use case will be inline-java, which is a library to combine Java and Haskell programs. And yeah, let's get to it. We will start by looking at some of the problems of managing resources when programming, and then we will see how they manifest in inline-java. So when programming with resources, we have some basic operations that we need to do in a specific order. We need at least to acquire the resource, then use it. And after we are finished, we need to release it. And if we get the order wrong, we probably will have problems. Or if we forget any of the steps, we also will have problems. So one first kind of error could be to release the resource and try to use it afterwards. In this case, most likely the program behavior will be undefined. Another kind of error is having resource leaks, which is when we use the resource, but afterwards we forget to release it. And it depends, what happens depends on how often we forget to release the resource. But if we do this often enough, then it will lead to some resource exhaustion in the system, and the execution will probably have to be interrupted. And another kind of error that we can have, I call the late release, which is when we make the garbage collector or some other subsystem responsible for releasing resources. And in the following picture, what we have is a representation of two regions of memory. One, say, is managed by the Haskell garbage collector. The other one is not managed by the garbage collector. So in this case, our resources are going to be buffers in the foreign heap. And we are going to assume that the Haskell side can request buffers in this foreign heap and get pointers to those buffers. So while the execution of the program advances, we can ask a pointer, then we can ask another. At some point, because the garbage collector is responsible for releasing these resources, when the garbage collector runs, the pointers are, the buffers are released, and the memory in the foreign heap is available again. And what could happen in this situation is that the memory in the foreign heap gets completely used, and now the system is about to fail if the garbage collector doesn't run soon enough. And this is an intermittent failure because it's undetermined, because whether the garbage collector runs depends on conditions that are determined at runtime. It could either succeed if the garbage collector runs at this point, or fail if if it doesn't. Another characteristic of this scenario is that there are other processes or other threads trying to use the foreign heap. So if they also try to acquire memory from the foreign heap and the heap is full, then they will fail. And it will be very difficult to recover the system in those cases. So now let me introduce you to inline-java and how these problems play out there. Inline-java, it's you can think of inline-java as a library that allows you to embed Java code in your Haskell modules. It provides primitives to create Java objects and to use them. So one of such primitives that we have is reflect. Reflect takes a Haskell object and converts it to a Java object. And when it finishes the conversion, it returns a reference to the newly created Java object. So in the picture of heaps, it looks like this. There's there's a heap managed by the Java runtime, and here is where Java object lives. And then we have a pointer on the Haskell side. And when we want to use the pointer, or when we want to use the Java object, we have another construction, which is a quasi-quotation. The quasi-quotation includes some code inside that we can use to express some we can use to write some Java code. And in this case, the Java code can refer to references that are available on the Haskell side. And inline-java will know how to pass these references to the Java runtime so this code can be executed. So when the Java code finishes execution, then inline-java arranges to return back to Haskell a reference to the new value that has been created on the Java side. And this is how it looks like in our picture of heaps. Now we have the result of the quasi-quotation on the Java heap and a new reference to it on the Haskell side. Now, suppose we are finished. We want to do something with what we computed on the Java side. We can then use a function called verify that will take the Java reference and will convert the object that it points to a Haskell value. And then we can do in Haskell anything we want with a value, for instance, printing it to the screen. And there is something very important that is missing in this program yet to make it correct. That is precisely deleting these references when we are done with them. If we don't delete the references, well, we have the same situation as before. The Java heap could get full. The garbage collector in Java won't be able to release the memory because it will think that it is still used from the Haskell side. And either other threads trying to allocate on the Java heap will fail, or the Haskell runtime will fail when it tries to allocate the next time. So this is how the problems look like in inline-java. It turns out that solving these problems is rather a hard problem. If we ask the programmer to remember to release every reference on that is created in a program, that's like an impossible task when the program is large enough. Think of tens of thousands of lines of code. So humanity needs help from machines. And in order to get that help, we need to write tools. So if we are programming in C, for instance, we are lucky. We have a fantastic tool that will detect use after freeze and memory leaks for us. This is a tool that executes the program. So provided that we have a good test suite that rehearses all the interesting paths, the tool can find the errors. But when we turn to the Haskell side, the landscape is more difficult. If we want to deal with use after free, well, we can reach to the garbage collector that will make sure that all the references that the Haskell site has are valid, and they will only be released when they are no longer used. But the garbage collector has the problem of late release, and that begs to go and look for other tools. When thinking about memory leaks in particular, often we think of the GHC profiler, which is a sophisticated tool that allows to analyze our programs, the performance and the memory that the program uses at runtime. However, the GHC profiler is not good for analyzing resource usage. It can only understand, it can only understand Haskell memory. And I think this is as much as we have currently of tools to deal with resource management. Now we could look at solutions in the language to deal with this. So one often side solution to deal with deallocating resources is the bracket function. The bracket function has 3 arguments. One is an action to acquire the resource. Another argument is a function to release the resource, and there's another function yet to use the resource. And the guarantee is that the release action will happen immediately after running the function which uses the resource. And the release function will be executed even in the case of exceptions. Whether the function completes successfully or not, the resource will be released. And this is how our Hello World program looks like with bracket. So besides not being particularly readable, just compare it with the version which doesn't use bracket, it doesn't solve really any of our problems, because it's perfectly possible to write a program with bracket that uses the resource after it has been released, as in this example. And it is also the responsibility of the programmer to remember to use bracket in the first place to acquire and to release the resource. So so we need to look for something better if we want to handle consistently the resources in a large code base. So another solution, which is quite effective at preventing memory leaks, is the resource team monad. The idea of the resource team monad is that it works more or less the same as I/O, but it provides a function to run it that guarantees that when you finish running the computation, all the resources that have been requested will be released. So then we modify our API to use this monad instead of I/O. And when we surround our Hello World program with a call to run resource-t, we get the assurance that at the end, when we finish the execution, all resources will be reclaimed. So this is an improvement over bracket. It doesn't prevent use after free, though. So if we were to return one of the references that we are creating in our program, then nothing will stop the programmer from writing some code like this. The compiler will be perfectly happy with this code, and it will fail the second time we try to use shref2. And there's another evolution of this approach, which would be to use monadic regions, where we have, again, a function, in this case, run safe IO, that will run our computation and will ensure that at the end, the references are released. But there is some type cleverness going on here that ensures that we try to do the same as before, returning a reference that has been released. Now the compiler will notice that when we try to use it a second time, this reference, this reference have been invalidated. And this is not a comprehensive list. There are other approaches, but I think it is representative of the trade-offs that we have to make in order to try to solve the problems related to programming with resources. So here comes LinearTypes, which it brings a new point in the design space. So to see how our Hello World program would look like with LinearTypes, we have to consider changing the meaning of some of our functions first. Suppose that the Java quasi-quotation, instead of just running the Java code, would also delete automatically the first reference that is being used. Right, so now JRef1 is deleted when the Java quasi-quotation finishes running. And we will do the same for ray5. So now ray5, when it converts the value, after converting the value, it will delete the reference that we were given as input. It is still possible to have leaks, because if we forget to use a reference, then it will never be released. It's also possible to have use after free, because if we use a reference a second time, it will be invalid. But we can bring here the new language extension, LinearTypes. And if we change our monad now from IO to a linear variant of IO, the compiler will start checking that the variables that we are binding in our tuplog must be used exactly once. So if the compiler can check this, then it's not possible to forget to use a reference and have the compilation succeed. So in principle, use after free, in principle, memory leaks aren't possible in this setting. And if we look at use after free, it isn't possible either, because we would need to use a reference twice in order to do use after free. And this is also something that the compiler will prevent us from doing, given that the references must be used exactly once. So now, when compared to the other approaches, this is a static guarantee. We are not asking the programmer to remember anything or to be careful of what is being returned from our computations. But it introduces some noise or some things that we need to be careful about. One of them is that this restriction applies to all variables that we are binding. So what about hello world? Hello world is a regular Haskell value. Why should it be used exactly once? Well, because of this, we can change our API. So ray5 returns a non-restricted value instead of just a normal value. So what is an unrestricted value? Well, it's a value that is annotated with an extra data type constructor, and it tells to the compiler that it is fine to use the value as many times as the programmer wants, 0 or more than once. And another concern that using values exactly once brings is that what happens if we want to use a reference more than once? In this case, there are at least two options. One mechanism is to duplicate the reference before using it. Now we have two copies of the reference, and we can use each copies on a different use. Another option would be to pass along the references that we get as input instead of deleting them. So we return them in the result. And this is something that we rehearse with ray5. So here Reify takes a JRef2 reference, and it returns a JRef22 reference along with the hello world result. And the JRef22 reference is points exactly to the same object that JRef2, and the compiler will insist in that we use it exactly once. So now we have to be mindful of deleting it so compilation can succeed. Which approach is better? Should we duplicate before using, or should we make our APIs so they pass the references along? Well, it's something that a decision that can vary case to case. In the case of Reify, we are not even sure which is the best approach. So we are supporting both and see in practice what happens. And we are not done yet, because you might know already that the do notation is not allowed for the linear I/O monad, and Twig had to invest like a year figuring out how to make a language extension that would allow to use do notation for linear monads. And that language extension turned out to be qualified to, and it's also going to be available in the next version of GHC. And to use qualified to, we need to qualify our to keyword with a module alias that will say which operations should be used in the desugaring of the do notation. And now I think we are finished with converting our example to using linear types. There's one extra detail to consider, which is what happens in the unhappy case that we have an exception in the middle. So if the execution is interrupted, say, when we are evaluating our Java quasi-quotation, if we don't take measures, there's nothing that will take care of deleting our references JRef1 and JRef11. And to deal with this, we resort to a solution similar to resource-D. We wrap our program with a function with local frame that will guarantee that when we reach the end of the execution, all the references that haven't been deleted will be deleted at that point. And given that we are introducing this function with local frame, that begs the question, what happens now if we try to return one of our references? And the thing is that the types won't allow us to do that, because with local frame, it's supposed to return an unrestricted value. And to the compiler, this means that the value can't be one of the linear references, that is, references that must be used exactly once, and they can't be either, and the references can be either hidden inside a data structure or a closure that we return. So we are safe. And when we compare linear types with or the solution with linear types with the solution with round resource-D, there's very little syntactic overhead for the static guarantees that we are getting from the compiler. So, but the best part is that there's plenty still to ponder and to have fun, because because the little syntactic overhead that we have, there are ways to reduce it. One bit of overhead is name shadowing. It looks like in order to please GHC, we need to come up with a new name every time we pass along one of our references or when we duplicate them. And it's unclear whether we really need to use different names, given that our variables need to be used exactly once. So perhaps it's possible that the warning could be disabled for the warning about name shadowing could be disabled when using linear types. Another bit of overhead is that we have to be explicit in duplicating the references when we want to use them more than once. Wouldn't it be fantastic if the compiler could decide alone how many times the variable needs to be duplicated and then duplicated for the programmer? It looks like it should be possible. At least one could think of a compiler plugin that would scan the linear tuplog and decide that here we need to duplicate the reference once and do that for us automatically. So another bit of syntactic overhead is having to pass these references explicitly. So in the case of RAIFI, we need to pass shref. We need to bind shref2 again when we invoke RAIFI. And there's people also wondering whether we could have the programmer just write the straight thing and have the compiler fill the details. And some discussion about that is happening at this GitHub repo, which you are invited to check. And there's more. We have to sometimes we will want to combine our inline-java API with other APIs that we have in Haskell. However, because inline-java now is using a linear monad, the question raises whether or how we combine this linear monad with other interfaces that are not using linear types. So if I wanted to implement some logging in our hello world example, then probably we would need some glue to compose the two interfaces together. And this is just an example of a problem of composing linear and non-linear functions that could express still many times. And there are efforts to try to unify the code that is perfectly, the code that we have in the base libraries that is perfectly linear, but GAC just doesn't know it yet. And with this, my friends, we reach the end of the talk and the down of linear types in Haskell. I hope you have enjoyed, and I look forward to the Q&A session to answer your questions.